So we have discussed about the situations of constant wall heat flux and constant wall temperature somewhat qualitatively, that is how the wall temperature and how the bulk mean temperature varies with x. But question is, what is the rate of heat transfer, that is what is the Nusselt number. So we need to discuss about what is the Nusselt number for thermally fully developed flow. So there may be situations when the flow is hydrodynamically fully developed, but it is not thermally fully developed. Like, let me give you an example. So this is hydrodynamic boundary layer. And this is thermal boundary layer. So if you have a fluid say of value of high Prandtl number, then what will happen? This delta will be significantly more as compared to delta T. So the hydrodynamic boundary layer will grow very fast. So the hydrodynamic boundary layers will merge here and the flow will become hydrodynamically fully developed. So from here to here there is a region when the flow is hydrodynamically fully developed but not thermally fully developed, right. So that kind of problem is known as Gray's problem. This kind of problem is actually in the purview of advanced level of convective heat transfer. So we will not come into that here. There is another type of problem where the flow may be both hydrodynamically and thermally developing, like this region. But in this particular course we will be concentrating on this region where the flow is both hydrodynamically and thermally fully developed, and we will evaluate the Nusselt number for that cases. So hydrodynamically and thermally fully developed flow through parallel plate channel. Case 1, constant wall heat flux. So we have seen, so what answer can we expect for these types of problems? What are you assured of when you are solving a problem of thermally fully developed flow? We are interested about the Nusselt number. The Nusselt number will be a constant. That is what is expected. So if we do not come up with a constant Nusselt number, that means something is wrong in our analysis or approach. So the Nusselt number will be a constant and our objective will be to evaluate that constant value. So we have to keep in mind that, see what earlier cases we have studied for evaluation of Nusselt number, flow over a flat plate. Their Nusselt number was of the form of Reynolds number to the power something say half into Prandtl number to the power something say half or 1/3. This kind of expressions we have seen. So Reynolds number to the power m into Prandtl number to the power n. In general, for forced convection, Nusselt number is actually of the form Reynolds number to the power m into Prandtl number to the power n. But for hydrodynamically and thermally fully developed flow, for the internal forced convection, that is a special case where Nusselt number becomes a constant. But in general, if you have a situation, even the situation changes if the flow from laminar becomes turbulent. So then you have, you cannot work out those problems analytically, you have to deal with certain correlations based on experimental studies which engineers use for designing a system with a turbulent flow. I will come to one or two such expressions, but before that remember here we are assuming laminar flow. So constant wall heat flux. Now let us write the governing equation, the energy equation. This is our governing equation. Now tell what will be the simplification. So let us write it with a different color maybe. So in place of del T del X for constant wall heat flux, we can write dTm dx, which is a constant. What about this term? V is equal to 0 for hydrodynamically fully developed flow. So this will be 0. What about this term in the right hand side? Del T del X. Del T del X is what? Del T del X is equal to constant for thermally fully developed flow with constant wall heat flux. Because del T del X is constant, del 2 T del X2 is 0. So you can write U dTm dx is equal to alpha del 2T del Y2. Now we will change these variables from T to theta, the non-dimensional temperature which does not vary with x anymore for thermally fully developed flow. Why we want to change the variable? Because T is a function of both x and y, but for thermally fully developed flow theta is only a function of y but not a function of x. So theta is T minus T wall by Tm minus T wall. So you can write del T del y remember T wall minus Tm, these are functions of x. So with respect to y derivative those are like constants. So similarly the second derivative, and what is dTm dx? dTm dx is, what is that expression? Q double dash P by m naught Cp, right? So Q double dash, in place of P what is, let us draw a parallel plate channel. Let us say that the width is B and height is 2h with the center line is y equal to 0. So what is the perimeter? So before that let us write another step. What is m dot? M dot is rho u average into A into Cp by perimeter. So basically we have to calculate perimeter by area. So perimeter by area, what is perimeter? Or let us calculate area by perimeter, whatever, we will invert that. Area by perimeter, what is that? B into 2h by 2 into B plus 2h, right. Now we have to consider a limit while calculating this area by perimeter. What is that limit? Limit is that h by B tends to 0, because by definition the parallel plate channel, the width is infinitely large. So what we will do is, we will divide both numerator and denominator by B. So this becomes 2h by 2 into 1 plus 2h by B. So this will become h as h by B tends to 0, right. So when h by B tends to 0, this term is 0, this term is 1 and these two get cancelled. So it becomes h. So you can write dTm dx is equal to Q double prime into perimeter by area is 1 by h rho u average Cp. So u dTm dx is u by u average. So we are writing this equation, this differential equation. U dTm dx is u by u average into Q double prime by rho h Cp is equal to alpha, alpha is k by rho Cp into Tm minus T wall into d2 theta dy2. Okay. So then rho Cp gets cancelled, rho Cp, right. In place of Q wall what we can write? Q wall is h into what? H into T wall minus Tm. So we can write d2 theta dy2 plus it becomes H, so Q wall by H, yes, d2 theta dy2 plus U by U average into H by Hk equal to 0, right. Now you can non-dimensionalize this, right. You can define a new parameter y bar as y by h, okay. So if you define a new parameter y bar as y by h, then this will be d2 theta dy2 plus u by u bar h by k is equal to 0. So there will be a 1 by h square here, that h square coming here will make it h by k. So in a non-dimensional form this becomes what? This is the Nusselt number based on H. And what is this? This is the velocity profile. This is where fluid mechanics comes into the heat transfer calculation. So the answer how theta will vary with y will depend on what? Will depend on the velocity profile. Now there are many types of velocity profiles which are possible, like there may be a case when molten metal is flowing very slowly. So in that case the entire velocity profile may be almost uniform, and that is called as a plug flow or slug flow. So if you have a plug flow or a slug flow, that means uniform velocity profile, then what is u by u average? 1, right. So that is a very special case, very simple algebra to deal with. I am not working it out here, but please take it as a homework and complete it by yourself, that consider a plug flow with u by u average is equal to 1. Then complete the remaining derivation. I will do the derivation for a more involved scenario when u by u average is not equal to 1, but it is a fully developed pressure driven flow, that is Poiseuille flow. So for a plain Poiseuille flow, what is the velocity profile? U by u average is equal to 3 by 2 into 1 minus y square by h square. This was derived by Professor Shom when he was discussing about the exact solutions of Navier-Stokes equation. So you substitute that here. So this is like from the fully developed flow Navier-Stokes equation you can derive, there is no problem associated with this. So now what are the boundary conditions? This is y bar, this is non-dimensional y. What are the boundary conditions? At y bar equal to 0, what is the boundary condition? Yes? Y bar equal to 0 is the center line. What is the boundary condition for theta at the center line? Top wall and bottom wall are having symmetric boundary condition. So d theta dy equal to 0 at y equal to 0, it is the center line symmetry. And at non-dimensional y is equal to 1, that is the wall. What is theta? Remember the definition of theta, T minus T wall by Tm minus T wall. So theta is 0. So with this you have d2 theta dy2 is equal to some function of y, let us say this is f y bar into Nusselt number with a minus sign. So d theta dy is equal to minus Nusselt number integral of fy dy plus some constant C1. So when you integrate you will get theta is equal to so this is let us say f1y right. I have just written it generically. This integration is very easy because this is a simple polynomial. I do not waste time by doing the integration. I want to give you the framework in which you can just put the numbers and values. So you can evaluate the constant C1 and C2. You can evaluate the constant C1 C2 by using these two boundary conditions. But does this solve the problem? You have an expression for theta is equal to a function of some function f2 Nusselt number and y. These are all non-dimensional y, so make this as y bar. These are all non-dimensional y. But this does not tell you explicitly theta as a function of y because you do not still know what is Nusselt number, what is the value of the Nusselt number. In fact, obtaining that is the objective. And remember that although I have written it as a function of Nusselt number and y, actually Nusselt number is separated from the function of y. It is Nusselt number into some function of y, because I mean it is not mixed with y. Nusselt number is outside this integration. So it will come out to be Nusselt number into some function of y. Now you might argue that yes, we have used two boundary conditions for a second order differential equation. So what makes the situation that still the problem is not completely solved? One of the reasons is that actually this boundary condition theta equal to 0 at wall is not actually giving you any new information, because theta by definition is t minus t wall by tm minus t wall. So at wall theta will always be 0, that is the definition of theta. But it does not depend on whether it is constant wall temperature, constant wall heat flux, whatever. It is just a simple English sentence, T equal to T wall at wall. So nothing more than that. So if that is the case, then that is what that has been utilized here. So we need to close this problem by putting some additional constraint. What is that additional constraint? That additional constraint is the definition of bulk mean temperature, which we have not yet used. We have not yet used the definition of the bulk mean temperature. Maybe we will do it here. So now use the definition of Tm. this rho Cp is constant for this problem. So we cancel the rho Cp part. So we can write what is integral of u dA, that is u average into A. So we have integral of u by u average. What is dA? dA is, so if you have a parallel plate channel, like this, so what is dA? So at a distance y, you take a small strip of width dy. dA is dy into B. So dA is dy into B, and A is B into 2H. So integral u by u average, in place of t you can write Tm minus Twall into theta plus Twall. You can write, you can change the variable from y to y bar by putting this h within the derivative. So it will become dy bar. This is the function f, and integral from minus h to h is 2 into integral of 0 to h, because it is symmetric in the two sides. So that 2 and these 2 will cancel. So this will become integral of f theta into Tm minus Twall dy plus Twall right. We have absorbed the y by h within the derivative. So if that be the case, then what is, can you tell what is integral of f dy? Non dimensional. See, f is what? F is the velocity profile. So integral of f dy, non dimensionally it will become 1 from 0 to 1, right, because integral of u dy is u average into the height. So u by u average into integral of dy non dimensional is 1. So this is from the condition that u integral u dy is equal to u average into 2h. So u by u average integral, this will become 1. So this is equal to 1. So we can say that Tm minus Twall is equal to Tm minus Twall into integral of f theta dy. That means integral of f theta dy equal to 1. This is the constraint. So theta will be, now you can write f2 of Nusselt number and y bar. the functions f and f2 are completely known. So this will tell you what is Nusselt number based on H. Now normally we can calculate the Nusselt number on the basis of H, but engineers prefer to use a length scale which is called as hydraulic diameter. So what is hydraulic diameter? If you have a circular pipe, you have the actual diameter, but if you do not have a circular pipe, there is nothing called a physical diameter, but something equivalent to the physical diameter is called as the hydraulic diameter. So for a circular pipe, what is the physical diameter? Let us do it here. So what is the area? Area is pi r square. What is the perimeter? 2 pi r. So what is area by perimeter? So how can you get diameter from here? Multiply by 4. So this becomes diameter. Okay. So 4 into area by perimeter for a circular pipe is the actual diameter. For a non-circular geometry, that is some effective diameter which is called as hydraulic diameter. So hydraulic diameter, let us write it here. Is 4 into area by perimeter. So what will be the hydraulic diameter for a parallel plate channel? The half height is h. Area by perimeter we have already calculated. What was that? H. So 4 area by perimeter is 4h. So the Nusselt number based on hydraulic diameter is the Nusselt number based on 4h, that is 4 times the Nusselt number based on h. And if you evaluate it with all these numbers, I have given the outline, but if you now evaluate the value, this value will come out to be 140 by 17. So this is your homework. 140 by 17. Okay. So if you, so I have given the full framework. In this framework, just you have to do the integrations, integral f, f1, f2, all this, and once you substitute, you will get the value of this. This is the, so we can see that the Nusselt number is a constant for thermally fully developed flow. For this example, this is the value of the constant. We will stop here and we will continue in the next lecture.